You're going to be all right. So here we go. 3 2a. All right. Now, we discussed derivatives yesterday and what a derivative is, and it's just the slope of the tangent. We know that. But sometimes functions are not, they don't have a derivative at a specific point, okay? So we're going to talk about something called differentiability. I got to spell this right. Differentiability. That might be the longest word you write down today. It's in your math class. All right, so we're going to talk about differentiability. Now that is whether or not you can take the derivative of something. That's what differentiability is, okay? So we're going to find out that it fails at some point. So how f prime of a at a point fails to exist. We've already seen this. When we graphed the derivative of that line segment one, there were points in there where there was no derivative. When we graphed the derivative, we had open circles at those points, okay? So there are 4 ways that a graph will fail to have a derivative at a certain point. Here they are. Number 1. Anything that has a corner. That's really gross. Let me rewrite that. Okay? If a graph has a corner, it will fail to have a derivative at that point. Let me give you an example. Jack, you ready? Here it is. F of x equals the absolute value of x. Okay? We've seen this before. We actually talked about the derivative of this. Okay? When you graph this, this is your basic absolute value graph. And we said that the derivative on this side of the graph is what? This side, the derivative was what? -1. So f prime of x on this side was -1. And then we also did this side, and we said what was the derivative on that side? +1. Okay? You're doing great. At this point, at 0, there is no derivative there. What would you say the slope of the tangent line is there? It doesn't have a slope. The reason why is because there is a corner at x equals 0. Okay, so differentiability fails at that point, at all corners. That's why when we did that line segment one, did you notice they were corners? Corners are very sharp edges that don't have a derivative there. All right, number 2. So there's 4 of them. Here we go with number 2. Number 2 is something called a cusp. At all cusps, you will not have a derivative. Okay? So let me give you an example of a cusp. F of x equals x to the 2/3. Okay? Maybe you've graphed that before, maybe you haven't. Let's graph that on our calculator really quickly. Calculator. Y equals x to the 2/3. Okay, so let me show you what a cusp looks like. Have we talked about a cusp before? No. No? Ooh, how exciting. Okay, here it comes. I'll try and zoom in on that a little bit. All right, so we see the slope. The slope's changing, and then all of a sudden at 0, it does this interesting thing. And so a cusp looks like this. It goes, yeah, it's a curved V, exactly, okay? So for this graph, that's what it looks like. And at x equals 0, it fails because of the cusp. So anywhere you see a cusp or a corner, they will not have a derivative at those points. All right, number 3, halfway there. The third one is a vertical tangent. What is the slope of a vertical line? That's a trick question, isn't it? Undefined. Okay? So if something has a vertical tangent, that means it has no slope. Vertical lines do not have a slope. So something like this. F of x equals the cube root of x. Okay? If you were to go to your calculator and graph that, you could go to math, go to cube root of x, hit graph. Check it out. Ooh, do you see that right there? That was exciting. Did you watch it go? No? No one cares? Okay. All right, so when you graph this, it looks like this, and all of a sudden it goes like straight up and down, didn't it? Okay? So at x equals 0 here, we fail to have a derivative because the tangent line is vertical, and vertical lines have no slope. And if you have no slope, then you can't have a derivative because derivative is slope. All right, number 4. And then the last way that something will not have a derivative at a point if it's not differentiable would be a discontinuity. Any of your discontinuities. If there's a hole in the graph, okay, there's no derivative there because there's not even a point there. If you have a infinite, okay, or a jump. How about this one? F of x equals the absolute value of x over x. We've seen this graph before. Bless you. Do you remember this graph?
Yep.
Do you?
No.
Okay. Does anyone remember this graph? No? This is the graph that looks like this. It goes right here,
Oh, yeah.
and then it jumps. Has a jump in it. Okay? So here, at x equals 0, now it doesn't have to be at x equals 0. These are just basic graphs. They haven't been shifted or anything. At x equals 0, there is no derivative. Okay? F prime of 0 does not exist because there's no point there. There's a discontinuity at 0. So a lot of times when we take derivatives, we like to take derivatives of nice things like polynomials. Because polynomials are nice and curvy and smooth. There's no weird cusps or corners. We like to take derivatives of radicals because those are nice smooth curves. No discontinuities in them. All right, so here, this is what we're going to do. Number 1. Okay, we're going to show that f is not differentiable. I'm just going to abbreviate and write DIFF, not differentiable, at point P by using the alternate definition of derivative. Alternate definition. And if you're wondering what the alternate definition is, that's the one that is the limit as x goes to a, f of x minus f of a over x minus a. We're going to use that to show that our graph is not differentiable at a point. Okay, remember when we did limits? And the limit from the left and the limit from the right had to equal each other in order for there to be a limit there? Okay, that's the same thing with derivatives. The derivative from the left and the derivative from the right have to be the same in order for there to be a derivative at a certain point. So we're going to show, it's almost like a proof. Okay, so here's a graph. And let's say that we have the graph of y equals 2. That's a really straight line, huh? That's crazy. Y equals 2. Let's say that's 1. And then we have the graph of y equals 2x. Okay? So I have like a little piecewise function here. And I'm going to show that this graph is not differentiable at x equals 1. You can tell by looking at it, right? There's a corner there. There's a corner there, but we're going to prove it, okay? So here we go. This is what you're going to do. We're going to use this alternate definition, and we're going to find the limit as x approaches 1 from the right. The limit as x approaches 1 from the right. Okay? So let me show you how to do that. Do you know what the answer is going to be? Well, at 1 it's not, but on the right-hand side, what's the derivative on the right-hand side? Does anyone know? Nope. It's slope with the tangent. So what's the slope on the right-hand side? 2. 2x, right? The slope's 2. All right, so let's do it. The limit as x goes to 1 on the right-hand side. We're just doing this side, y equals 2x. So we're going to use the alternate definition. So f of x is 2x minus f of 1. I think we should do it this way. I just think it's going to be easier when you plug it in. So f of x is 2x. F of 1 is 2 over x minus 1. Okay? So we get the limit as x goes to 1, factor out a 2, reduce. The limit as x goes to 1 of 2 is just 2. And we knew that was going to happen because the slope is 2 on that side. Okay, I'm not going to make you do the alternate definition on the left-hand side. Okay, if we're going to do the left-hand side and we take the limit as x goes to 1 from the left, what is this going to be? 0, because it's the slope. Okay? So the slope on this side 0, the slope on that side's 2. We can say that at x equals 1, because these were not equal, 0 does not equal 2, then it is not differentiable. Okay? So on one side it's 0, the derivative. On the other side it's 2. Those aren't equal to each other, and so there's no derivative at x equals 1. Okay? Now, is it continuous there? Yeah, it's continuous there. If you plug in f of 1 on this side, you get 2. If you plug in f of 1 from the right, it's also 2. So it is continuous, but it's not differentiable. Okay. All right, so here we go. Let's do another one. Number 2. Are we running out of time? We're doing okay. Number 2. Then they're going to give you a graph, okay? They'll give you a graph that looks something like this. 1, 2, 1, 2, 3, 4, 5. And let's say they do this. They give you a graph that looks like this. Okay? And they'll ask you this question. This is such a weird question, and I don't like it. I don't like that the book does this, but I want to get you ready for the homework. It says, at what point or points, at what point is the function differentiable? I'd rather ask, where is it not? You know what I mean? So at what point is the function differentiable? Now, what they want you to say is they want you to give intervals of x. So they want you to say it's differentiable from -5 to +1, except where? At x equals -2. Okay? So that's what they want. It's weird. I'd rather ask you, where is it not differentiable? But they're asking, where is it? So I would say everywhere on this graph, from here to here, except at x equals -2. Now you could also write that -5 to -2 union -2 to 1. Do you like that or no? No. You did that in Ham. A lot of people don't like that though. Okay? And then they'll ask you, why does it fail there? And you would say what? It's a cusp. Perfect. You would list one of your 4 reasons why it fails, and that would be a cusp. Okay? Let's do one more and we'll call it a day. Number 3. All right, suppose I have this graph. 1, 2, 3, 4. And let's say the graph goes like this. From here -5, -3. Solid. Okay. And the same question. Where is this function differentiable? It is a function, passes the vertical line test just fine. So where is it differentiable? That would be from, I would say, -3 to 5, except at what? At x equals 1. And x equals 1, and then what's the reason for that? It has a discontinuity. You don't have to say what type of discontinuity it is. It is a jump, but we don't have to know that. Okay?